Hello everyone and welcome. Today's topic is the impact of climate change on the hydrological cycle. Over the next few minutes, I'll walk you through how climate change is reshaping the way water moves through our environment. Let's begin with the basics, the hydrological cycle. This is the continuous movement of water on, above, and below the surface of the earth. It starts with evaporation, where solar energy turns water from lakes, rivers, and oceans into vapor. This vapor rises and condenses to form clouds, that's condensation. Eventually, the clouds become heavy and release water in the form of precipitation, rain, snow, or hail. Finally, water either runs off over the land surface into rivers and oceans or infiltrates into the ground, replenishing groundwater. Let's begin by clarifying a common confusion, the difference between weather and climate. The figure on this slide shows it quite clearly. On the left, we see weather. This refers to the short-term state of the atmosphere. For example, a rainy day or a sudden cold front. The temperature graph below shows frequent fluctuations. Weather can change within minutes or hours. On the right, we see climate, the long-term pattern of weather conditions in a particular region. The image of a tropical landscape symbolizes a stable, predictable climate, and the temperature graph below shows a relatively stable line over years, not days. So in essence, weather is what you experience now, and climate is what you expect based on long-term observations. Now, what is climate change? It refers to persistent, long-term shifts in these climate patterns, largely caused by human activities like burning fossil fuels, cutting forests, and releasing industrial emissions. Unlike daily weather changes, climate change is about broader and lasting alterations in temperature, precipitation, and extreme events happening over decades or even centuries. It's one of the most pressing challenges humanity faces today. This slide shows us the basic mechanism of climate change. On the left, we see the causes, activities like burning coal, oil, and gas, and deforestation. These actions release greenhouse gases like carbon dioxide and methane into the atmosphere. In the center, the greenhouse effect is shown. These gases trap heat that would otherwise escape into space. The trapped heat warms the planet, causing what we call global warming. The IPCC reports a 1.5 degrees Celsius rise in global temperatures since pre-industrial times, a change already linked to major climate disruptions. On the right, we see the consequences. The Earth's average temperature has already risen by 1.5 degrees Celsius compared to pre-industrial times. This warming drives sea level rise, disrupts ecosystems, and increases the frequency of extreme weather events like floods and heat waves. Now, how does all this affect evaporation? Higher global temperatures directly influence evaporation. In tropical regions, evaporation has increased by about 2 to 3% per decade. During heat waves, this effect becomes even more intense. As more moisture is pulled from the soil, we see significant soil drying, which impacts agriculture. Plants also face more stress, which reduces their growth and yield. And with more water vapor in the atmosphere, the greenhouse effect becomes stronger, creating a dangerous feedback loop. Climate change is also altering how, where, and when it rains. In monsoon regions like South Asia, rainfall intensity is projected to rise by up to 30% by the end of the century if emissions remain high. We are already seeing a rise in extreme precipitation events. Some areas have recorded a 50% increase in heavy daily rainfall since the 1950s. Climate models predict that high-latitude regions and tropical monsoon zones will get wetter, while dry subtropical areas may become even drier, intensifying drought risks. With more intense rainfall, urban flooding and soil erosion are becoming common. Cities are struggling to absorb the water quickly enough, leading to flash floods. At the same time, altered river flows are disrupting agriculture, making irrigation less reliable during key growing periods. Even more concerning is groundwater depletion. In regions like India, Pakistan, and Bangladesh, water tables are falling by up to 1 to 2 meters each year. This puts long-term water security at serious risk. All of these hydrological changes lead to wider consequences. Crop failures due to erratic rainfall patterns and dry soils threaten food security. Water shortages are hitting both urban and rural populations, raising the risk of conflicts over access to this essential resource. Ecosystems are suffering too, wetlands are drying up, biodiversity is shrinking, and the services these ecosystems provide, like flood protection and water purification, are being compromised. Despite the challenges, there are engineering and policy-based solutions that can help. Rainwater harvesting allows us to store excess rainfall and use it during dry periods. This can reduce both water stress and flood risk. Precision irrigation techniques can dramatically reduce water use in agriculture, improving efficiency up to 95%. Reforestation restores degraded land, promotes groundwater recharge, and stabilizes soil. And finally, integrated water management policies, combining engineering, ecological, and regulatory tools, are essential to adapting to climate-driven hydrological changes. To wrap up, global temperatures have risen by 1.5 degrees Celsius since pre-industrial times. Extreme rainfall events have increased by about 50% in many regions. And evaporation is climbing by 2-3% per decade in the tropics. These trends clearly show that climate change is already transforming the hydrological cycle, and the time to act is now. Thank you for your attention. The insights presented here are drawn from IPCC reports and leading scientific studies. Let's continue working towards solutions that ensure water security and sustainability in a warming world.